My name is Melissa Hines. I'm from the Department of Chemistry, and I'm here to tell you about public speaking for scientists and engineers. And obviously the first question is why am I the one to tell you about this? Well, back when I was a sophomore in college, I realized two things. The first thing was I hated public speaking, and I was really bad at it. And the second thing was, if I wanted to be a professor, that had to change, and it had to change really quickly. So at that point, I started paying attention to public speaking to try and figure out how people do it well, how people do it badly, and how to enjoy it. And I am here to tell you that, okay, it took a few years, but actually public speaking can be a lot of fun. Speaking about your own science can be a blast. There is nothing better than standing up in front of an audience and telling a great story. And there's also nothing worse than standing up in front of an audience and bombing. So I want to try and keep you from doing the latter. Okay, so why should you care about public speaking? Well, there's some really good reasons for this. And the biggest reason, according to your parents, is that you need a job. And if you're going to get a job as a professional scientist or engineer, you're going to have to give a job talk, particularly if you're at the PhD level. And before you give a job talk, you're probably going to have to go out to conferences and tell people about your science. And that's also important. But really, one of the most important reasons as a scientist, as an engineer, to learn how to give a good talk is because today most science is transmitted orally. And one of the really scary facts is that 55% of scientific papers receive no citations within 5 years of publication. So half of the papers that are being written are not being read. So the way you get people to read your papers is you go out to conferences and you give talks about them. Because a talk is essentially an advertisement to try and get people interested in your science and to get them to go back and read your papers. So a talk is really a high-level overview of what you have done in the lab just to get people interested in it. It doesn't include everything that you've ever done in your research. So the first thing you need to do when you have to give a talk is you have to plan your scientific presentation. And that sounds obvious, but let me tell you what most people do when they have to give a scientific talk is they open up their laptops and start writing at slide 1. And that's a really bad way to give a talk. You have to plan your message if you want to be effective. And so what you want to be doing is you want to be telling a story, not presenting a report. This is so incredibly important. Now, what's the difference between a story and a report? They're both ways of transmitting information, right? But when you're telling a story, you're trying to get people interested in a story and you're trying to keep people's attention. On the other hand, you know what it's like when you write a report because as an undergraduate, you've written in many of these things. And there you're just trying to get as much partial credit as possible. So you take everything that's supposed to be in the report and somehow you cram it in there in one place or another and hope that the poor person who's reading it is going to find that information. Very, very different mindset. A report, everything is crammed in. A story, you're worried about whether the audience is going to be paying attention to you. And when you give a scientific presentation, there's no law that the audience has to listen to you. And if you're boring, they won't. They'll be on Facebook. They'll be doing lots of other things. So you have to figure out what your story is going to be. And to do that, you need to ask yourself, why should anyone care about your work? So big picture. If your research works fantastically this summer and next year and for the next 5 years and the next 10 years, then so what? What's going to come out of it? And you have to start your talk by telling us that. Are you trying to invent a new battery that's going to make cars go farther? Are you trying to clean up pollution? Are you trying to find out something about the fundamental nature of the universe that no one has ever learned? What is it that your research is going to do if it works? And start there. Then you have to plan your take-home message before you do anything else. Now, what do I mean by the take-home message? This is incredibly important. The take-home message is what people remember about your talk 2, 3, 4 weeks later. So think about a talk, think about a class that you took 3, 4 weeks ago. How much do you actually remember from that lecture? I'm a professor. I know how much you remember. Not very much. Okay? If you're lucky, you remember sort of the general ideas behind it. You remember a few concepts. You don't remember any numbers. You don't remember any detail. But certainly if someone were to ask you a question about that, then you would know where to go look to find out the answer. So the take-home message is 2 sentences, 3 sentences, really big picture about what you have done. And that's what you're trying to get across to your audience. And you can't just say it once, because if you just say it once, people won't remember it. Your entire talk is crafted around the take-home message, because you're trying to get people to remember it for a long time. The second thing is, and this is quite important, is you need to know your audience. You will give a different talk to a different audience. Okay? Your message has to be tailored to the audience. So never overestimate your audience. And that's what happens when people first start giving scientific presentations, because for so long you've been sitting in lectures and feeling sort of bamboozled and overwhelmed. And so you think that that's the way people should feel during good talks. And they shouldn't. Okay? If you're giving a good talk, most everyone should be following along. And they should be following along normally. You're not supposing that they're sitting there and concentrating with all their might. They're just sitting there. They're eating sandwiches and cookies. And so you have to be at a lower level, and you have to be more engaging than you would normally think. It can't have lots of numbers in it, can't have lots of equations. You're just giving essentially an advertisement, an introduction. If people are really interested, they're going to go and read your papers. So what I want you to do at the end of this summer, and whenever you give a talk, is I want you to aim your talk at the median person in the audience. Don't just aim it at the one person who knows your field really well, because if they know your field really well, chances they're on Facebook and not listening to you. You want to be trying to get the most people that you can interested in your research. So I think most of you are going to be giving a talk at the end of your summer program. So let's do an experiment and let's find out who the median person or the median audience is in this room. So how many of you are chemistry majors? Raise your hand. Okay, median person is not a chemistry major. I don't want to see any of those nasty arrows being pushed, okay? Because most of these people aren't going to understand it. So how many people are material scientists? Raise your hands. Okay, not the median audience, so watch it with those phase diagrams. The rest of the world doesn't understand them. Okay, how many of you are theorists? Raise your hand. Oh, there are only 2 of you, so you guys got to be really, really careful. It's not you. How many of you are physicists? Raise your hands. Okay, but still not the median audience. How many of you are biologists? Okay, so how many of you are majoring in either science or engineering? Aha, so the median person is majoring or has majored in science or engineering, and that is the common denominator. So your talk has to be aimed at that audience. You can't assume anything more, so you're at a bit above a general New York Times audience. You've got a good audience, though, because you know that they all like science and engineering, so that's on your side. But the details you need to be really careful with. And some of the things you take for granted, like organic chemists, those little, diagrams of benzene and stuff, most people don't understand those. You have to speak more broadly. Okay, so now you're going to be telling a story. Let me tell you about the trap that a lot of people fall into when they give scientific presentations. You have been in the lab for all summer, maybe longer than that, maybe years, doing science. You're like a detective. You're leaving no stone unturned, no idea untested, looking at the tiniest detail with your little magnifying glass. That's great. That's why we all do science. However, that's not how science gets rewarded. So, great quote, in science, the credit goes to the man who convinces the world, not to the man to whom the idea first occurs. What that means is, it doesn't matter what you discover in the lab, how well you understand it, unless you can communicate it to other people. Because if other people don't find out about it, it doesn't matter, and we shouldn't be funding you. We should just let you stay at home. Because the whole thing about science is advancing knowledge. So you can't pretend like you're Sherlock Holmes when you're giving a scientific presentation. This is not what you're going to be doing. Instead, when you're presenting science, you're someone very different. When you present science, this is who you are. Who is this? Atticus Finch, the best defense lawyer ever. Okay? If you don't know To Kill a Mockingbird, I know you know Law and Order. So think about it that way. So, Law and Order, when the defense attorney stands up, what is the first thing they say? The first thing he says is, Tom Robinson is innocent. This is the take-home message. He doesn't stand up and say, you know, Mrs. Marple in the study with a candlestick was doing such and such. No, he wants to get across the idea. He says, Tom Robinson is innocent, and I will show you Tom Robinson is innocent because of A and B and C. And that's the way he starts out. That's the way you need to start out because you're trying to get your take-home message across, and you have a limited amount of time, and people have a limited amount of attention. So no detective stories. Another way of looking at this is who is the audience for these two different things. For Sherlock Holmes stories, the audience was Watson, and he was captive. He had to sit there and listen to all this detail about cigar ashes and nonsense. And come on, Sherlock Holmes was a cocaine addict, so it was not the most interesting thing in the world. On the other hand, here you have a jury, and a jury is a very fickle audience. And if you don't hold their attention, boy, they're going to find your defendant guilty. Okay? So you have to hold attention, you have to tell a story, you have to be engaging. That is the secret behind giving a good scientific presentation. Okay, so let's talk about the structure of the talk. If I were to take a poll and to ask you what should be on the first slide of your talk, 90% of we would say it should be a title slide. Okay? Don't do that. The reason is, if there's a title slide, you're going to put the slide up there, you're going to read the title, you're going to read your name, and then flip past it. Doesn't do you any good. Instead, you want the first slide, which is the most important slide, to be engaging and to capture people's attention. So make your first slide an introduction slide and have the title on the top. This is by far the most important slide in the entire talk. This is the only one where you're basically guaranteed that the entire audience is going to be paying attention. And if you blow it here, you've blown it for the rest of the talk, and no one's coming back. So it's got to be important. It has to give the big picture, what's going to happen in 10 years if my research is completely successful. Or the way I like to put it is, it has to pass the grandmother test. Now, what's the grandmother test? The grandmother test is when you go home after this and you see your grandmother and she says, so what did you do this summer? And you have to tell her. If your grandmother is like my grandmother, then she's dead. Oh, okay, let's not think about that. Okay, so she's dead and is not a scientist or an engineer. So you have to be at a really low level. Grandma does not do equations. Grandma probably does not have a science or engineering background. If you're lucky, Grandma reads the New York Times. So your introduction has to be at the level of the New York Times to a general science and engineering audience. And honestly, if you learn to speak at that level, you will be a fantastically successful presenter. That is the level at which most presenters present. Also, it's going to have to introduce your take-home message. Why is that? Well, remember that you're trying to make sure that everyone in the audience remembers your take-home message for weeks, if not months. And the only way they're going to remember that is if you say it multiple times. So it's going to come up again and again. This is where you introduce the take-home message. During the talk, you will reinforce it. You'll come back to it at the end. That doesn't mean you're saying the same sentence over and over and over, like this is some weird foreign language course, okay? You find different ways of saying it, but you're trying to get across this message. Okay, so let me give you one example that I've used as an introduction. Hi, my name is Melissa Hines. I'm from the Department of Chemistry at Cornell University, and I'm going to tell you today about the quest for atomically flat silicon. Now, how did we get interested in this? Well, we got interested in this for a sort of strange reason having to do with the microelectronics industry, and this has to do with the performance of transistors. Now, we all know what transistors are. They're just little electrical switches. So you switch the flow of current between the source and the drain. And in a transistor, the way you switch this current is you apply a voltage or a potential to the gate. What's interesting about today's transistors is that the gate is actually insulated from the body of the transistor by a very thin layer of glass or silicon dioxide. So what's the problem? Transistors work, but they don't work as well as they could. And one of the problems is because that as this current flows, these electrons actually flow in a very thin, a few nanometer thick region called the channel. And since the electrons flow in such a thin region, if there is any roughness between the glass and the silicon, like this, then the electrons will scatter off. And if they scatter, they don't get to be signal. So we set out to try and learn to make this interface as flat as possible. So what causes the roughness? Well, basically any stage in the fabrication can cause roughness, including the most stupid stage, which is where we come in. Simply cleaning off the silicon wafer can cause roughness here. So one of our goals is to learn to clean off silicon perfectly and to make it perfectly atomically flat. And if we can do so, we know we'll make better transistors. So that was our first goal, to make atomically flat surfaces. But as we got interested in this, we said, hey, what if we can replace this gate with chemistry, with molecules? Then we would be able to make electronics with chemical or biological functionality. But in order to do that, we need to make not only atomically flat surfaces, but atomically perfect chemistry. So what I am going to show you today is that surprisingly, very simple chemistry. Chemistry in a beaker can be atomically precise and can cover the entire surface with exactly the same thing. So let me show you that. So that would be an introduction for an hour-long talk. Obviously, for your talk coming up, it's going to be a little bit shorter, but it's really big picture, okay? You don't know exactly what I'm doing from this, but you understand the goal if everything works. Okay, so that's the introduction. Now, if I were to take a poll and to ask you what comes next, 80% of you would say the same thing. And you would say, next comes the outline of the talk, right? No, do not put in the outline of the talk. Why is that? Outlines are very important, but an outline of the talk is like the table of contents of a book. And the reason you have a table of contents in a book is because if you're only interested in chapter 7, you're going to turn ahead to chapter 7. In a talk, if you're only interested in point 7, guess what? You're sitting through points 1 through 6 before we get to 7. You can't click ahead. So there is no reason to show us an outline. It doesn't do us any good. We will not understand that. So I started giving this talk about a decade ago. After I did it, I would listen to the end of summer presentations, and sure enough, 80% of the students would put in an outline of their talk. So it doesn't just work for me to tell you, don't do this. Okay, so let's think about this a little bit more deeply. What are you trying to do? You are trying to tell a story. So let's think about, how do you tell a story? Well, let's think about the greatest storyteller ever. Who is that? Well, I mean, we could come up with a lot of different names, but I would say arguably one of the greatest storytellers ever was Homer, right? Because we're still telling his stories thousands of years later. So I want you to ask yourself, how did Homer tell stories? I'm sure he used PowerPoint. But you really think he started out by saying, hi, my name is Homer, and I'm going to tell you the story of the Odyssey. Before I get going, let me give you an outline of my talk. First, our hero is going to finish the Trojan War. Then he's going to travel for 10 years. He's going to visit the Lotus Eaters, blind the Cyclops, shack up with Circe, pass between Scylla and Charybdis, listen to the sirens before the whole darn thing away. And third, it just isn't very entertaining. So don't do this. You need an outline. Keep it to yourself, hidden, okay? Don't show it to us. Okay, so what comes after not showing us the outline? There are a number of different things you can do. However, one of the most common things after this is to show us an experimental or a computational slide to tell us what you've done. I know I certainly get pretty pissy when I'm half an hour into a talk and I still can't tell whether the speaker is a theorist or an experimentalist, so I'd really like to know what it is you did. There are other ways of doing this, but I suggest tell us about what you did here. And what you want to be doing is keeping it simple. You are never trying to impress people. People are not impressed by overwhelming amounts of detail. People are never impressed if they don't understand. Keep it simple, give us an idea, not lots of detail. The other thing is that photos are rarely helpful. So if you see this photo or this photo or this photo, they all mean something to me. They don't mean anything to you. You're just sitting there going, why is this man wearing white gloves? Okay? So you can't get any detail out of this. We want to have line drawings, just the important parts. So let me give you an example of the kind of stuff that I would include in an hour talk. So let me tell you a little bit about what we do. Our experiments are really quite simple. What we do is we take a surface, initially very rough and bumpy, stick it into a beaker and etch it for a while, then we fish it out and put it into an ultra-high vacuum scanning tunneling microscope. And what we're basically trying to do is to take pictures of our surface after it's been etched to try and understand the chemistry. So once we have this picture, how do we understand which reactions went on? Well, we have an equally important computational aspect to our research that goes something like this. It's really very simple. All we do is we make a model of our surface, in this case silicon, in our computer, and the silicon can have any structure. So it can be perfectly flat, like these terraces right here, and flat silicon has a single silicon hydrogen bond pointing straight up. Or maybe it's rough, it has some steps on it, and this particular surface can have two types of steps. One has a dihydride structure hanging off the end. The other has a monohydride structure coming off the end. Where these intersect, there's a kink, and so on and so forth. Now, as a chemist, what you would expect is that these different sites, the dihydrides, the monohydrides, will all have a different reactivity. You may not know which one is the most reactive, but our simulation includes the possibility of them all having different reactivities. And initially what we do is we just guess random numbers for the reactivity of the terrace and this step and this kink and so on and so forth. And then we ask our computer, if those are the correct reactivities, what would our etched surface look like? So we model the etching. And then we look at what our computer says. We compare it to what is in the experiment. And then through an iterative process, we adjust these etch rates until our computer simulation looks like our experiment. And as we go on, you'll see how this works. So very, very simple ideas, computational, no equations, just the general idea. Experiments, line drawings. Don't impress me by how big and bulky your experiment is, just simple ideas. Okay, so after the experimental or computational comes the part that's actually the easiest, which is going to be the body of the talk. And this really is the part that you're going to be most comfortable talking about. There are a couple of things to take care of, but let me just tell you a little bit about the body. So again, you're trying to tell a story, not give a report. So this is important. You don't have to tell us about the experiments in the order that you did them. Because remember, you're Sherlock Holmes. You didn't know the end result when you started out. So chances are you did a lot of experiments that didn't work. Don't tell us about those, okay? Just pretend that you did everything correctly. And tell us about the experiments in the order that you wish you had done them, which is probably exactly backwards from the way you did it, okay? This is what everyone does. You're not cheating, you're not lying, but you're telling us a logical, orderly story. Now, the hard part is going to be getting between the different experiments you did. So it's easy to explain one experiment. The harder part is to string these together to make them into a story, and I'll talk about this in a moment. But the easiest way of doing this is to have a series of questions that are raised by each experiment, and then that leads into the next experiment. Importantly, as I have said quite a few times, no detective stories. Remember, you've already given away the big picture, you've already given away the take-home message. You're just trying to show people why you know what you know. Okay, so let's talk about the typical structure of the body. Let's say you wanted to synthesize a new polymer to be used in some kind of biodegradable Coke bottles, okay? So what do? You go into the lab, the first thing you do is you synthesize the polymer. So you'll have a slide or maybe a couple of slides talking about your synthesis, and then you'll talk about the results of it and the conclusion that you got from this experiment. So I synthesized my polymer using this, and I got a 95% yield. Now you want to talk about your next experiment, so you have to say what question came up. So I synthesized this polymer. The obvious question is, did I synthesize what I thought I was going to? And so you ask the question raised by the first experiment, and that leads you into your second experiment, which might be characterization of the polymer, and you'll talk about the experiments that you did to do that. You might do GPC, might do NMR, something like that. Talking about each of these different slides is going to be very easy for you because that's what you've spent all your time doing in the lab. The hardest part is making the transition from here to here. So you need to know what this question is going to be, and it's either going to be written on the slide or you have to know it in your brain because you're going to be practicing your talk. So after you do the characterization, well, then the question is this material good for Coke bottles? So then you have to go and you have to do your third experiment. You have to test it, do mechanical properties, something like that. You get results from this and conclusions, and that takes you off to your conclusion slide. So again, this is the easy part. Knowing how to get from one to the other is the part that's going to require you to give some thought. Okay, so typical structure of a body slide. I know many of you have been, all of you have been in talks before. You know basically what to do here, so we'll go through this quickly. The general idea is that the title has to summarize the main point of the slide. One thing to keep in mind is that when people are listening to talks, usually they're trying to pay attention. All right, sometimes you're not. But sometimes they lose their train of thought because something came in on Facebook or whatever, and they inadvertently got distracted, and they want to rejoin the talk. You have to keep in mind those people. So some people missed a little bit of what you said. Maybe they didn't understand it. They need to be able to rejoin the talk. And that's why you have informative titles up at the top. In the middle, you have your data. And so you can imagine, looking at this data here, I have plotted quality factor as a function of bulk atoms over surface atoms. And you're probably going, what in the world does that mean? And that happens to everyone. And so because of that, you always want to have at the bottom of the slide sort of the take-home message about the experiment. So in case you don't remember what quality factor is or why I'm plotting it this way, the data strongly suggests that the surface losses dominate. Okay, so this is the main point of the slide. This is the conclusion. Alternatively, instead of having the conclusion down here, you could have the leading question that is leading you to the next slide if you're having trouble getting the flow to go. The one thing that varies a lot from field to field is whether or not you put references down here. So let's say first why there are references here. No one thinks that you're sitting there with pencil and paper going, oh, I've got to write this down. Okay, no one does that. The real reason the references are there is to show that you read other people's literature, in case particularly they're in the audience. So you're trying to show, oh, Parpia and Craighead, yes, I really like them. They are nice people, fund my research, and Ruckus. So it's mostly the people at the end that are important. It is the PIs. So never say D.W. Carr et al. That does not work very well at all. Don't worry why these are in different colors. It has to do with why I gave this talk. But if you give references, just remember people are looking to see who did the work, in part so they can go home and look up the background literature on this. So if you are an organic chemist and you don't put references down at the bottom, I think you get stoned to death and they just never invite you to do anything. Physical chemistry, it used to be no one put them down. It's becoming more important. You have to ask people in your lab how important this is and which references absolutely have to be at the bottom. Obviously, if you know that Parpia and Craighead are in the audience, good thing to put on the bottom of the slide. Okay, so introduction, experimental computational body, and that leads us to the best part, conclusions and acknowledgments. I strongly suggest that you have one slide that has both the conclusions and the acknowledgments on them. And there are a couple of reasons. Oh, and I should say the conclusions need to be very simple. This is going to be no more than a couple of lines. I'll give you an example in just a minute. And obviously, it's going to reiterate the take-home message. But the reason that I like to have the conclusions and the acknowledgments on the same slide is if you're out of time and somehow you took a little bit too long in your talk, you can just put this up there and you can leave it there and you can let the audience read it. Otherwise, you're going to have to put up the conclusions and then go to the acknowledgments. And that's not something good to be leaving up on the slide. So let me give you an example. This is a conclusion and acknowledgement slide that I used after an hour-long talk. So 2 main points, 2 subpoints. This is probably one of the most verbose conclusion slide I ever used. For your talk at the end of the summer, 1 point, maybe 2 point. Very, very simple. Acknowledgements. When you give the acknowledgements, if these people are not in the audience, I just say, and I'd like to acknowledge the wonderful graduate students who did the work. If the people are in the audience, you have to be a little bit more verbose, but this is not the Academy Awards. A sentence, 2 sentences, that's fine. Let's not talk about their experience in first grade or anything like that. It is vital that you put down the funding agencies at the bottom, and it's truly vital. You don't have to say anything else. I just say, and I'd like to thank the nice people who paid the bills. But it is important that it be down there, and you need to ask your PI who needs to be credited, because it's usually more than just one group. Okay, now the part that gives me the most nightmares. I shouldn't say that. But it's handling questions. How do you deal with the questions? Because your talk, you can practice and practice and practice, but then the questions, you never know what people are going to ask. So let me give you a couple of things to think about. First, make sure you understand the question. One problem is that the people asking the questions, obviously they're out in the audience, many times they're sitting in the back row. It can be very difficult to hear them. And a lot of times scientists, engineers, they come from different countries, so they may have an accent. So it can be difficult to understand it. It is always fine to ask, did you say blah, blah, blah? If you're not sure exactly what people have asked, it is also fine to rephrase the question. And you can say, well, are you asking such and such and such and such? And if you got it wrong, they will say, no, no, no. But if you got it right, and sometimes I rephrase it in a way that makes it a little bit easier for me to answer, then it does help you in answering the question. So don't worry about that. Very common not to understand the question. Second thing is, you need to keep your answers short and to the point. This is not your license to pull out the 4 backup slides that you didn't have time for. Your answer should basically be no more than a minute. If someone, and this is never going to happen at Cornell, I promise you, if the person asking you a question is arrogant or rude or hostile, the most important thing for you is not to be arrogant or rude or hostile back. Because at the point when someone is being a jackass, the entire audience is on your side, because probably this person does it every week, and they're sitting there going, oh, I can't believe he did it yet again, he's embarrassing us. If you are arrogant back, then the audience is like, oh, let me out of here, it's 2 of them, okay? So you just have to smile, you just have to continue the conversation. Now, what about some useful answers for awkward questions? So there's someone in my department who always asks the speaker, regardless of what the topic is, he always says, have you thought about the implications of the fluctuation dissipation theorem on your research? And the person will be like, I'm synthesizing polymers. And so they're like, no. And it's always fine to say no or I don't know when someone asks you a question, but I know that you're not going to want to do that. I hate doing that as well. So one answer to have in your back pocket is just to say, well, that's an interesting point. I'll have to think about it, okay? And that works for so many questions. It's the easier way of saying, I have no flipping idea. Okay? So then the other thing is sometimes you'll get someone who's really interested in your research, and they'll ask you a question and you'll answer it, and then they'll ask a follow-up question and you'll answer it, and then they'll try to go for 3. And at some point you have to cut this off. And basically after one follow-up, you do need to cut it off. And the way everyone does that is just by saying, maybe we should discuss this offline, okay? And after the talk, they'll come up and talk to you, but that gives other people a chance to ask questions. Okay, so the last thing I want to tell you about is watch out for ringers. And so let me tell you a story that was told to me when I was a graduate student. I had this solid-state physics professor, great guy, really sweet, really nice, complete genius, okay? And so he comes in to talk one day, and he says, you know, I want to tell you a story about a talk I gave when I was a young assistant professor. I thought I was a real young punk back then, and I got the call. I got the call to go to Bell Labs to talk about my research, and that was like Mecca. So I go out to talk about some research that I had just completed, and I was feeling really proud about this because it used this new technique known as Wannier functions. And so I didn't think anyone in the audience would have known about it, and I'm pretty studly for doing this. So I'm going on and I'm telling my story about my research, and then a hand goes up in the audience, and I say, okay, yeah, what's their question? And he's like, yeah, I was wondering, did you normalize those functions? And for those of you who haven't had quantum mechanics, this is just a very straightforward procedure. So did you normalize these functions? And he's like, no, that's the great thing about Wannier functions. They don't need to be normalized. You can just use them out of the box, and they work. And so he goes on, blah, 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 and then he turns around, and there's another question. And it's the same guy. And he says, yeah, got a question? And the guy's like, yeah, I was just thinking, I was thinking that it would just work so much better if you normalize these functions. I just think that it would make your research be, and he's like, no, you don't understand. Wannier functions don't need to be normalized. That is what's good about them. No normalization, Wannier functions, okay? No normalization. So he goes on, blah, 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 and then he turns back around, and it's the same hand. And the guy, yes, can I answer it? And he's like, oh, well, I was thinking normalization would just make your results. And he's like, no, you don't understand. They don't need to be normalized. They just don't, okay? Accept this fact. It is what it is. And then he turns around, and he's talking and talking, and he looks back, nothing, talking and talking, talking. And he makes it through the entire talk, okay? And so after the end, the person who invites him comes up, and he's like, who was that guy in the audience with all of those questions about Wannier functions? Who do you think it was? Wannier, okay? So, A, if there is someone famous, we now have the internet. Look up what they look like so you recognize them, okay? But the bigger answer here is never be arrogant and never be hostile. There's always someone who knows more than you do. Talks are a great way to get new ideas, and giving a talk is a way of exchanging ideas and of learning. It's not some weird gladiator contest where you're trying to kill everyone else, okay? So just go into it with an open mind that people are going to give you great ideas. Okay, so let's talk about the intangibles about giving a talk, because that's just as important as the structure. So presentation style is very important. You have to speak firmly, slowly, and confidently. Okay, ladies, if you stand up here and talk in a little girl voice, guess what people will think? They will think you are stupid. It's not fair, it's not right, but you need to learn how to project. You need to learn to be confident. It is amazing how much difference that makes. So you need to practice. You can easily fill this room with your voice. I can do a room with 500, okay? So you can learn to speak loudly. You need to speak slowly. Many people are not native English speakers, so they're trying to understand. If you have an accent, pay attention to the consonants and really try and spit them out and alliterate. It will help your accent be understood. You need to look at the audience. When I took macroeconomics as a junior, the lecturer gave all of his lectures with his eyes closed. It was the most creepy thing in the world, and that is all I remember about macroeconomics. Now, I know some of you will be scared in talking. You can't tell whether I am looking at you or not looking at you. If you're worried, don't look at people's eyes. Just look at their heads. Look a little bit above. Never make the mistake of looking below the head, okay? It's creepy as well. So keep your eyes up there, especially if you're a guy, okay? You also have to learn to use the pointer, the clicker, and the microphone. And if you've never done this, I know it looks easy, but it's much less easy. If you have never been tethered to a microphone before, you should probably practice this because it's really easy to trip on it. Fortunately, I have done this. Pointer and clicker. I strongly suggest you use two. Pointer in one hand, clicker in the other. The reason behind this is it's easy to get confused in the middle of the talk and to click when you want to point and point when you have to click. Okay, the pointer. If you've never used a laser pointer before, when you go and you try and point at something, what you might find is that as you try and point and hold your hand stable, it's going to get more and more jittery, and the more you try and hold it stable, it does not work. So if that happens to you and you look like you are on crack, all you have to do, don't try to hold it stable, just start making circular motions, make linear motions like this. One of the things when using a pointer is remember to look at what you point at. I had a student who would point at things and then he would turn around like this. And then everyone is like, okay? So, and even if you don't do that, he would do this. You know, and then it just doesn't make any sense, okay? So that's when you're using a laser pointer, which is most of what you're doing. If you are in a smaller audience, I strongly suggest that you use a mechanical pointer. It actually works much better. It's easier to use. It does require a little bit of thought, though. So for example, with a mechanical pointer, you are going to point. You are not going to beat into submission, okay? We should not actually hear you pointing. Same thing about pointing and turning. Don't do this, okay? That does not work very well. The microphone. Microphones do not go where you think they go. Never place a microphone down here. We will just hear whether you had lunch or not. The microphone goes very high. It goes right about here. It never goes on your collar, because if it's on your collar and you turn your head, you lose the microphone. So it needs to be dead center. Women. A lot of times you will go to put the microphone on and you'll be like, oh, it doesn't work on my shirt. And that's true, it doesn't. They're usually for men, and men's shirts button in the opposite direction. So what you do is you take the microphone off, the little clippy thing pulls off, flips upside down, and puts it back on, and then it works on your shirt. And be sure to leave it that way to screw the guy behind you. Everyone should know this. Okay, if you are not wearing a button-down shirt, suppose you go and put on a sweater or a dress, just grab a big old handful right here and clip directly onto that. You're going to your interview talk, definitely wear something with pockets, because you usually have to put the transmitter somewhere. Wear a blazer, wear pants, something like that. There is nothing like having a clicker and a pointer and then trying to balance the transmitter on your nose. It just doesn't work, okay? So dress appropriately. You need to expect the unexpected. If at all possible, use your own laptop, especially if you have movies. PowerPoint is designed by idiots. Check the equipment right before the talk, because it's out to get you. And definitely bring your talk on backup media, maybe a thumb drive, and also bring your own pointer. I was a graduate student at Stanford, and you would not believe, you think Stanford, rich university, right? Oh my gosh. So for the first 2 years while I was a graduate student, they didn't have a regular pointer. Instead, what they had was an industrial mop handle. And for those of you who have never been an industrial mopper, these things weigh like 20 pounds. And so the poor speaker would be like, trying to wrestle this thing into submission. And we would go and we'd talk. The fact would be like, this is really embarrassing. Can't we get something like a regular pointer? And so they're like, oh, sure, sure. So then they asked Jim Coleman to bring in one of his fly fishing rods. And this thing must have been 25 feet long. So now the speaker's back here, and the pointer's way over there. And so it didn't work. So just buy your own pointer. Lasers are inexpensive now. Green works better than red. Red doesn't always show up. But bring something with you. And practice. You have to practice your talk. You have to practice it out loud. You need to practice standing up. And you need to practice it straight through. That's how you learn to give a good talk. Timing is critical. Going over time is rude, and if you are at a conference, people will shut you up. So when they say 13 minutes, at 13 minutes and 30 seconds, they can just pull the plug on you, and they're not going to be nice about it either. Going under time is equally bad. We once had a woman who came to interview for a faculty position at Cornell, and she gave a stellar talk. It was just, everyone was like, oh, so good. But it was only 30 minutes long, and it was supposed to be an hour talk. And so what happened is the people came out of the talk saying, wow, she did really great science. Too bad she didn't do as much as everyone else, or else we'd hire her. So if she had practiced her talk and gotten the timing right, she'd be standing up here and not me. So Okay, rule of thumb. This is a really hard one because people have different styles when they're giving PowerPoint talks. Somewhere between a minute and a minute and a half per slide is really good. You don't want to be sitting there going click, 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 because people have to digest what it is that you are talking about. And so just try and keep it at a sane number of slides. The conclusions and the acknowledgments are typically a little bit faster, but on the other hand, the introduction is something it's typically a little longer. So going too quickly will annoy the audience, even though it's otherwise a great talk. And of course, there should be only one concept or experiment per slide. So the nuts and bolts, I've already told you, you want an informative title and self-contained content. You want to be using short phrases, not complete sentences. And the reason for this is if you put a complete sentence up on your slide, people will read it. And if they're reading, guess what they're not doing? Listening to you. So only short phrases is a way to help people remember what you are saying. No garish or gratuitous colors. My general rule is don't use any of the primary colors, so don't use bright red, bright green, bright blue. Just tone it back a little. So instead of bright red, go for a maroon. Instead of a bright blue, tone it down a little bit. That will make you look better than 95% of the other speakers. You don't have to be perfectly color coordinated because let's face it, you're talking to scientists and engineers and we're pretty challenged in that area. And then, of course, you're going to put your conclusion or your question at the bottom of the slide. Okay, so this is a truly hideous slide that I pulled from one of my long ago students' talks. And so we'll just go through how hideous this thing really is. And there are just so many things that don't work about this slide. For example, he says images of twist-bonded wafers, and we have no idea what kind of images these are. Maybe you know what, it looks like electron microscopy, probably, but TEM, SEM, oh, maybe it's AFM, who knows? And then there are all of these numbers. Look, numbers at the top and numbers at the bottom. So what do these numbers mean? And then down here at the bottom, this is like a paragraph. And so you're sitting here trying to read this, but it still doesn't help you make any sense of it. So obviously there are things that you can do to make this better. I think one of the real things that's missing from here is you're talking about twist-bonded wafers, and there's no real explanation of what it is we're looking at. So an improved slide might look something like this, where now I have a sketch of the experiment and the buried dislocations. And I know I haven't gone in enough detail for you to understand what's going on, but this is a sketch of the experiment. And now I'm talking about small angled buried dislocations, and I've labeled the twist angle and the dislocation spacing. I have a conclusion, and so I have done everything that I have told you to do, except for one thing, and that is when you look at this slide, your eye just doesn't know what to do. It doesn't know where to start. It doesn't know where to end. It doesn't have, there's no real train of thought on this slide. And that's the one good thing about PowerPoint. And so with PowerPoint, you can use animation. And I strongly encourage you to do this as a way of leading people through complicated experiments or leading people through your data. And so for this, I would just start out and talk about what the experiment is. And so I'd say we make these buried dislocations. Then we take TEM images of them. And here are the images. And you can see as we increase the twist angle, you can see that the features get smaller and smaller. And this is actually quantitative. So as we increase the twist angle, we decrease the dislocation spacing, or we increase it going in the opposite direction. So animation is really your friend, and it's something that you need to get comfortable with, and that's why you need to use a clicker, because otherwise you have to keep running back and forth to the computer. Okay, one thing that students used to spend a lot of time thinking about was which of the pre-prepared slide formats that come with PowerPoint should you use. And out of a RU program of 30 students, 28 of them would use the same slide format, which is this one. So what's wrong with this slide format? It's too colorful. What was that? You can't read the title. Look, you can't read the title down here. And that's because you've written it in white. So if you write it in black, you're going to have the same problem down here. Anything else? Yeah.
Is distracting and unrelated to the topic?
Yeah, it's distracting and unrelated. This has nothing to do with anything that is going on. It might look cute the first time you ever see it, but we've all seen this, and we've seen this for 5 years. So don't do this. Instead, if the most interesting thing about your science is the background of your slide, don't give a talk, okay? So just use a plain background because you want your science to come out to the foreground. So there are two choices. One is you can use a dark solid color like I do, black, or potentially you could use dark blue. I am a microscopist, that is why I use black, and actually black looks much better if you don't use these white backgrounds. But black is going to give you the highest contrast if you're a microscopist, so that's really important. There are problems with this. If you use a black background, you have to redesign all of your graphs so that they're labeled in white to make them stand out. That's what I do. It works really nicely. It looks better. You may not want to do that. One thing to be careful about is it's very difficult to match colors between programs. When you look at your talk on a laptop, it will look great. When you look at it coming out of one of these piece of junk projectors, it will look awful, and the colors will look nothing similar, okay? So black is always black, white is always white. Everything else is up to the projector. And so two things that look like they're the same blue on your laptop may be very different coming out of a projector. The other possibility is to use a light solid color, and really it should be white. The advantage there is you can use images that are prepared for the journal directly, and it's easier to give your slides to someone else, like your lazy PI who doesn't want to make his own slides. And he undoubtedly uses white. So black or white, black is better, white is easier. It's up to you. Okay, size matters tremendously. Remember, you're giving a talk to a broad audience, including lots of famous professors. Famous professors are old, bad eyesight, can barely hear, okay? Keep that in mind, and they sit in the back just to annoy you. Okay, so they're blind as a bat. You need to use really big type. So, big type is important. This is Helvetica 24. Never, 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 never use anything 14 point or smaller, and that is even really small. For things like that, font sizes that look garishly big, like 24, are probably what you need to be using. Everything on the slide must be legible. And I know you're like, well, duh. Okay, I want to see those graphs when you're presenting them. I want the labels on the graphs to be legible. Showing me a graph where I can't read the x and y axes is silly. I don't know what the experiment is. Everything must be legible. So, how do you test this? The easiest way is to use the 8-foot test. With your laptop, you get up, you stand up, you walk back 8 feet, you look at the slides, and you say, is this legible at 8 feet? If it's not big enough. If your eyesight's really good, you need to be at something like 10 feet. Really important that people be able to read this. Okay, font is also important. You need to use a font that is designed for this purpose. A font that is designed for headlines. A font that is easy to read just instantaneously. So it turns out that there are two types of fonts. There are what is known as the legible fonts, and there's what is known as the readable fonts. Legible fonts are for headlines. Readable fonts are for extended blocks of text. Are you going to have extended blocks of text in your slides? No. Who said yes? Okay, I'm not coming to your talk, so there. Okay, so how do you tell? Huh? I will be. So, but you can give a better talk. Okay, so how do you tell legible from readable? You look at the corners. You look up to see if there are little curly cues. No curly cues, curly cues. The curly cues are called serifs. You want to use a sans serif or without serif font, not a serif font. So typical sans serif fonts would be something like Helvetica, Avant-Garde, Verdana, Techno. Readable fonts, Times New Roman. This is what you write your thesis in. This is what you design your graphics in. Almost all publications, almost all papers have figures designed in Helvetica or Arial. So I suggest you use something like this. Okay, so what you are going to do is not use the serif fonts. So font color is also important. We're going to do an experiment. I'm going to show you 4 pieces of text. You tell me which one your eye is drawn to. Which one did you look at first? The black. So your eye goes to the black one. Let's try it again. The yellow. Let's try it again. White. Okay, one more time. The one on the bottom. Okay, so your eye is naturally drawn to the highest contrast image. You don't even have to think about that. So you are going to use that concept to make your slides easy to understand, because you want people to look at your slide to see the important points, the subpoints, without you having to explain it. Okay? So you are going to use contrast to help you do that. So what you're going to do is something like this. You're going to use contrast and size to prioritize your information. So immediately your eye is drawn to these big blue colors. It's all in a large, bold sans serif font. And I have chosen my colors so that the most important content has the highest contrast. It's blue on white. The secondary information is going to be red on white. So having black text on white is always the best. I know you're going to say, oh, it's boring. But remember, we're interested in the science, not your ability to choose colors. Dark colors on white are okay as long as they're not ugly dark colors. White text on black is okay, but realize that white text on black looks like it's smaller than it is. So you need to increase your font size to keep it legible. Never, never use colored text on a colored background. It doesn't work. There are well-known optical illusions with it. Because of projectors, it's often ugly. So just use a few colors and keep these ideas in mind as you put your slides together. Presenting graphical data. I know that almost all of you have taken a lab course, so you have all gone through this. You need to remember all of it, so we're just going to do this as a worked exercise. I'm going to show you a graph. You tell me why it sucks. What's wrong with this graph? There are so many things wrong with this. So I've heard a lot. So like this, what is this? This exponential, that's really nice. Look at how the data, you can barely see it because it's on a colored background, so you can't see the yellow. It's squished into this narrow piece of the graph. There are these lines that are distracting going across. There's this series 1, series 2, which you have to then go back and try to figure out how that goes with this. But there is one thing above everything else that really sucks about this graph, and I think you all realized it as soon as you saw it, and that is that Excel sucks. And as soon as you see this, you say, this hoser used Excel. They can't even bother to use a real graph and to do something that looks professional. If you're going to be a scientist and engineer, I strongly suggest you get something better than Excel. And if you insist on using Excel, at least learn how to turn it into a reasonable graph, okay? So we can take the exact same data and present it in a much better way. And there's so many reasons why this graph is better. The one thing that I would say about this graph is I made this probably 10 years ago, and if I were to do it today, I no longer leave my legends over on the right-hand side because it makes it harder and slower to understand. What I would do would be to take this legend data, and I would say 2.5 microns, 4 microns, 5.5 microns, 7 microns, so you can immediately see the colors, the legend as you look at the data. But you all know how to make nice graphs, so don't let me see any sucky graphs at the end of the summer. Okay, one last thing, presenting equations. How do you present equations in a way that is accessible, that everyone understands? There are a few simple rules. Rule number 1, don't do it, okay? No equations. Rule number 2, there is no rule number 2. Don't show us equations. Equations just don't work very well because either the people in the audience already know the equation, and if they know the equation, why are you showing it to them again? That doesn't help. And if they don't know the equation, it is very unlikely that they are going to understand it after you put it up. I have violated this rule in the past, and almost always I have lived to regret it. So what can you do instead of putting up an actual equation? One thing you can do is you can show a graph of the equation, or you can fit the equations to the data. That helps a lot. You can sketch the physical concept and just talk about the ideas behind it. There's so many different ways of talking about equations without actually showing them. Now, after my lecture, if I stop right here, all the theorists will come up and say, no, really, how do I show equations? Because I have to show equations or people will think I'm stupid. They won't, I promise you, but if you have to show an equation, the only thing you can do is label the parts of the equation so that people can read the equation like a sentence. So if you had a kinetic equation like this, you can say, well, the reaction rate is equal to the production of C from A and B minus the spontaneous decay of C to form D. But if you're going to say that, why do you need the equation? That's the only way to do it, but really, if you're ever going to show an equation, something more complicated than F is equal to ma, and F is ma we already know, think about it twice. Okay, so to wrap up, let me give you a couple of closing thoughts. The first thing is you need to practice your talk out loud. I don't care how good you are, you have to practice it out loud. I practice my talks every time before I give one. Before I give a lecture, I give the lecture beforehand and I do it out loud. It's very important. Don't make the mistake of sitting there with the forward key going, oh, I know what I'm going to say, click, I know what I'm going to say, I know what I'm going to say, I know what I'm going to say. That does not work. The hardest part about giving a talk is not about explaining each slide. It's about getting the flow from one slide to the next, and you have to practice it. It is so much better to practice it and to make your words flow than to stand up in front of an audience and look like an idiot, because you will feel like an idiot. So get in the habit of practicing. You also need to practice your talk on friends. If it's an important talk, you've looked at it so many times, you're not even seeing it anymore, and you don't necessarily see the typos. Let me give you an example. When I was a graduate student, I had to give a very important presentation to our funding agency, the Office of Naval Research. And it was not until the question and answer session at the end with our program manager that I was informed that there are two ways of spelling naval. Only one way actually funds research. The other way, you can guess which way I spelled naval. That was incredibly embarrassing. Don't do that. If I had talked in front of my friends, someone would have known how to spell naval. Talk to people outside of your group. Ideally, you want to talk to someone who's never seen your research before. So then you can understand, you can hear what's completely new, what they don't understand. Because there are things that you say day in and day out in your lab that everyone else does not pick up on as quickly. So ask to speak in an outside group meeting or speak to someone who's not a scientist. It's really very helpful. But one of the most important things is that when someone asks you to listen to their talk, or when you ask someone to listen to your talk, tell them that you want honest, constructive criticism, and you should give it. If there's something that doesn't work, you need to tell your friends, because it hurts to hear it, but it's better to hear it from your friends than not to get the job. So you have to really give good feedback to people and tell people, be honest with me, what sucked, what didn't suck. So with that, that's my thoughts on giving a scientific presentation, and I'll be happy to answer any of your questions.